Hi, welcome back. In this lesson, you will learn how to recycle different workflows you already have in our software and connect and adapt them to your own purposes. Connecting workflows or different steps of your product development processes unleashes the value you get with our software. Like this, the expert knowledge is not isolated in different departments or in different software or in different workflows, but they can communicate with each other and we have all the expert knowledge integrated into one larger workflow. You just did the first steps course and are at the beginning of your journey, so we will start with a super simple example that will still teach you how to recycle and connect different steps of the product development process. As you already know the different lessons of the first steps course, we will take some of those workflows and use them. So we will take the design of experiments and optimization lesson, and we will take the FM analysis lesson, and we will connect those steps. So first, you will create a parametric CAD design. Then you will parametrically extract reference geometries and use them for an automated FEM analysis. This FEM analysis is used to evaluate the displacement in the design, and with this evaluation value and the different parameters for our parametric CAD design, we can now do a design of experiment and choose which design is best based on our simulation results fully automatically. This lesson is especially interesting for development engineers who work in more than one world and are not just interested in CAD or FEA, because here we connect these two worlds and design changes are automatically considered in the FEA simulation. In this lesson we start off with a clean canvas, so just open a new document and save it somewhere on your computer. Alright, now please open the FEM analysis and the design exploration lesson. First off, we will copy this part of the design exploration lesson, drop it on our empty file, and then also this part. You could also copy everything, but I don't need all the annotations and images and so on. So I'm going to go with this. I'm going to put it up here because we need this later. Alright, and now we copy the FEM analysis lesson. I opened the starter here, so this is empty, but I can just copy the solution from down here and also drop it here. Okay, and you can delete the grouping and the solution here, we don't need that. So now we copied the two workflows we want to recycle and connect, but there are some adaptations we need to make. First of all, if you remember from the design exploration lesson, here we evaluated our design by the surface area to volume ratio. We do not need that anymore. It's not a very realistic value. It was just like helping out to understand what is happening, what the logic is like. But here we would like to evaluate the design by the displacement or the maximum displacement in the design. So let's define that. We have here our model that we need to enable, and we can delete the internalized model. We do not need that anymore. Okay, so we have run our simulation. Let's just check if that looks good. Yes, looks great. And now we want to evaluate the displacement. Get the displacement response component here. We need to enter the load step. And let's go with the tolerance like that. And now we want to evaluate the results of the solved model. And here you can see that we have our displacement value here. So this is the value we will use to evaluate our designs. So let's say we change our design and go here and change, let's say, the length. You probably notice that nothing in our FEM setup here changes because, of course, we haven't connected anything yet. We use the internalized values from the FEM lesson, and those are set values, or not values, like bodies and surfaces, and they're not parametric, they don't change. So now we have to connect the two workflows so that actually if we pull on our slider to change the length, also the FEM setup, everything's in there changes. Let's start with the design space. I can make this invisible. So this is the design space from the FEM lesson, and here we have the non-design spaces extra for our topology optimization. We don't need that for this example. It makes it a bit more complex than necessary. So let's delete the non-design space. Also here, the non-design space solid part, not necessary. And also the internalized stuff we will delete because we want everything to be parametric. So here, instead of the internalized input, we will use the output, this cantilever beam from our CAD generation. Okay, as you see, now it changed, and this is what will be meshed. We will run the FEM simulation quite a few times, so I will make the element size a bit larger, just so that it won't calculate for such a long time. It's a bit less accurate, but for this purpose it doesn't really matter. All right, let's check what happens here, and if something red, that means there's an error and we have to check what's going on. First indicator usually is to hover over the exclamation mark and read, but in this case it doesn't tell us so much, so let's plug a panel here to the info output and see what's going on. So our RBE spider doesn't find dependent grid points, and there are two reasons for that. One is here we have a solid part where the RBE spider can't find nodes on there because it's empty, we deleted it. But also we have a target body for our RBE spider that's still this internalized input from before. We need to make this parametric. So we need to automatically generate the reference geometries. That's the next step that we will do. So we will use our body and extract this surface for the support, and we will extract this surface to apply the RBE spider to, and then the forces via that. Okay, so first we will deconstruct the body to get all the surfaces. And now if you calculate the area of each surface, you also get the centroids of those surfaces. And here you see that these two surfaces we want to get are the surfaces with the smallest and the largest x value. So we will deconstruct those centroids and then sort them by the x value. So the values that we want to sort are the surfaces. Let's move these out of the way. And the keys we want to sort by are the x values. And now we have the surfaces in the order. So if you decide to toggle through them, you see, okay, this is the first one, then these are next, And the last one is the one we want to apply a force to. Okay, so list item with the first is good to get this support surface. And then we can just reverse the list. And again, pick the first item. And just like that, we have the force surface here. All right. So here we have our two surfaces, and we can now connect it. We have our reference geometries. So this is for the support. I can actually put it down here. And this is for the force. So now let's check what changes in our FE setup. This is for the connector spider now. And actually this point has internalized values, so it's not parametric, which is not ideal for our situation. So let's delete that point, and if you don't enter anything here, always the center point of your target will be chosen, which works just fine for us in this situation. Okay, let's check if it actually works and everything is connected. So if we visualize this, we can see that our RBE spider is connected to all the nodes. And if we now go back to the beginning and pull, let's say, the length slider way down, we have to wait a bit. You can check here with the zoom to running where we are, and then this should update to our new geometry. Great, as you can see, we have our new length here, and the load step automatically now refers to the recalculated reference geometries that are automatically selected. So now we have all we need to set up our parameter setup and the design exploration, which we copied somewhere here. All right, so for our parameter setup, we want the interval and the length, and we want the response for the maximum displacement. So let's define a response here. And we want to minimize the displacement. Okay. Let's actually call it displacement so we don't get confused. And also add that here to the parameter setup. Great, now our setup is ready and we can create and evaluate designs. I would say we start with something like 10, so we don't have to wait forever. And as you can see here, we have here our different intervals and length values, and they're all still pending. We haven't calculated them. Here the displacement values will appear. So I click on evaluate. This takes a little bit, but not too long. And you see here in blue where the workflow is calculating. All right, great. So we calculated 10 different designs, and now we can see the displacement values here. You can sort them. Now we have it from high to low or from low to high. And as this is the optimal design from these 10 designs, I want to load this design to check out what it looks like. All right, so you might have suspected that the ideal design is kind of short and thick if you want a minimum displacement, and this is what we get. And we can close the design exploration setup. Okay, so this is our connected workflow, and you have now here your CAD generation, your CAD design. Here we extract reference geometries. Then we set up the FEM analysis, and then we simulate and evaluate. And now just for fun, we're gonna change up the design even a bit more and get some more shapes here for our cantilever beam. So I would suggest we take a polygon and a circle, an ellipse. All right. And we can, let's make this invisible so we see something. Here we have those, and then we can enter planes and radii and so on. First, for our rectangle, let's delete this input and use this instead. That's an update that came in, so we can now make our life a bit easier here. And then use the same plane also for the ellipse, the polygon, the circle. All right, they're on the right plane now, but still kind of small. So let's use the radii here. Same with the ellipse, which is very skinny. So we could also say, okay, the second radii for the ellipse should always be half of the first one. So I guess that looks all right. And we can now make a stream filter where we enter all of our different curves. And depending on the index we enter into our stream filter, one of the curves will be selected. So we have 4 curves, so 0 to 3 would be the index slider. And here you can see that you can easily select the curves. All right. So now we can link what kind of base curve or what shape our cantilever beam should have to our parameter setup 2. And then enter this input in here. Make a bit of space. As you can see, we're recalculating again already here at the optimizer. So let's see what the result looks like, what shape we chosen. I didn't pay attention so much. Okay, this circle, cool. And now we can play the same game again. We go to our parameter setup just to double check. Yeah, we have the index in here too now. And now we can create some new designs. Those are the old ones we already tested. Make 10 new designs, and now you can see here that we have the interval or the radii, the length, and also the index. So we have 4 different possible shapes for our cantilever beam and can now evaluate the displacement. Alright, so we evaluated our 10 designs. Let's check which one is the best of them. Here we have the smallest displacement. We can load that in. Right, so this lesson showed you how you can very easily connect CAD design and FEM analysis. Of course, it doesn't stop here. So now you could also connect a topology optimization or a shell thickness optimization. But yeah, this gives you an idea of how it works, and connecting those other steps works in the same way. You make your parametric setup and then you can variate your design, evaluate your results, and so on. You remember here in this section, we did an automatic extraction of reference geometries from our design space. And here I want to give you a little outlook to a more advanced example and how it works there. This is an outlook about the automatic feature detection or reference geometry extraction. So here you see that if you have parts that are very different but somewhat similar, you can set up your workflow and then use it for different kind of geometries, and it works every time. In this case, we import the geometries first, then we generate the reference surfaces, then the part is meshed, RBE spiders are defined, boundary conditions are defined, and lastly the FE analysis is performed. And then of course this could go on with optimization, a topology optimization, whatsoever. All right, so let's look at these first two, the import geometries. We have this part and then also this one. And we extract the cylindrical surfaces and then use them for the RBE spiders. So we want to fix the bolt holes for our FEM simulation. And if I blend in this model, you can see that the RBE spiders are created and are connected to the center point of our bolt holes. And if I now choose a different bearing, so the second imported bearing, it takes a little bit, but it runs through again, and those other cylindrical surfaces are chosen. And then also you can see that the RBE spiders are connected to the center points again, and this would be a more elaborate example of the reference geometry extraction. In this lesson you learned how to recycle different steps, connect them to each other, debug what's going wrong, and adapt it to your purposes. I hope you wrap your head around how you can use and implement this in your big product development processes and are now ready to continue with larger workflows and your own parts.